Hello everyone, my name is Channing Deng from UW Medicine. Today I will be talking to you a Lagrangian data assimilation and UQ work on CS flows with Superfloe Parameterization. This is a joint work with Lan Chen and Sam Stelchman from UW Medicine. So let me first say that this work was supported by ONR Murray project on the topic of mathematics and data science for improved physical modeling and prediction of Arctic sea ice. So our goal is to simulate the Arctic sea ice flow dynamics. So here is a figure in the Arctic sea ice, marginal sea ice zone. So here in particular, this work, we aim to develop a framework for data assimilation and UQ with computational efficiency. And we try to gain computational efficiency through a superfloe parameterization, not through this parameter computing. So for this purpose, we use a highly simplified DEM model with cylinders. So in this domain, the flows are characterized simply by cylinders. And then our data assimilation goal is to recover the ocean current large-scale GB mode. So to simplify the DEM model, so the else flow evolves as follows. So this is the equation of the position, the center of mass of the flow, and the velocity, the angular position and angular velocity. And these two equations are from the Newton's law. So we have mass acceleration equals the force. The force consists of two parts, the contact force and the ocean drag force. So here the contact force consists of two pieces. One is the normal directional contact force, and then the tangential contact force, and again ocean drag force. So this is the Newton's law. Similarly for the torque on the angular velocity, the force from contact, the force from the ocean drag, and then the ocean, we use a simple linear stochastic model to describe the ocean. And also the Coulomb friction law is used to limit this tangential contact force. So I would say this is a super simplified model, and based on the existing DEM models, I would refer to the talks on more complex models in other talks on this workshop. So our goal here is to look into the data assimilation with superfloe parameterization. So here, what we are doing is that, so we consider a certain region with flows in this region. Say there are like 200 flows with 30 large flows in red. So these red cylinders are large flows. And then there are like 170 small flows. And then what we do is we parameterize these small flows as superflows. So like in the red, in the right plot, these blue cylinders are describing the superflows. So for example, what we do is here for this group of small flows, we parameterize it using this what we call superfloe. So each superflow has the preserve the physical quantities from the mass, for the mass, concentration, linear momentum, and angular momentum. So when we are trying to figure out this like position, velocities, angular velocities of superflows, we consider in this physical constraints. So connection to SPH. So the idea is well known. So it's based on merging the nearest small particles. Like, so we are trying to group together the labeling small flows. So we made it to be a superflow. So these are similarities to SPH. So the goal is similar, trying to reduce the computational cost. By the way, this is a similarity to the causing step of SPH. So for SPH, there are two steps. There is a causing procedure. So here we are connecting to the causing procedure. So the differences. So the differences is that the superflow are equipped with physical quantities like flow sizes, thickness, center of mass, velocity, angular velocity, and we are imposing the physics constraints to preserve mass, concentration, and momentums. In particular, locally, we are trying to preserve these quantities locally and then obtain the global one. And we preserve the long-term statistical kinematic quantities and the contact forces. So we also note that this superfloe parameterization is adaptive to different DM modeling systems. So let's look into a simulation. So simulation setting, so we consider this domain 50 kilometers by 50 kilometers on periodic boundary with periodic boundary. So the numeric scheme we apply is the simple Euler-Maruyama method, and the time marching step size is about 50 seconds. Simulation final time about 120 days, and the number of ensemble size 1,000. Observational variables. So we are observing the positions of the flows and then trying to recover the ocean current mode, the large mode, and noise and observational time step. And for the setting of flows, so the size distribution, thickness distribution are following these equations. And all these are empiric settings. And like the Young's modulus, other parameters, velocity and velocity scale. So ocean velocity scale is of 0.1 flows. And for the ocean, we set the ocean damping coefficients to be like 0.5, loss per number 0.1, and all other settings are here. So this is a very simple setting just for the purpose of illustrating the performance of the superfloe parameterization. So on the UQ side, so here, this is a slide showing the short-term behave. So what we are doing here is that we are considering three systems. So we consider a full system with 18 flows, totally 18 flows. And then these 18 flows, we assume that they are like six large flows. Then there are 12 small flows. So in the bare truncated system, all these 12 small flows are just simply removed. So we only use 6 flows to run the simulation here. And for parameterized system, what we are doing here, the 12 small flows are parameterized as 6 superflows. So here for the full system, 18 flows. For the bare truncated system, only the 6 largest flows. For the parameterized system, there are 6 large flows and 6 superflows. So, and then we run the simulation with the same initial condition, same setting for the also for the ocean. And then we observe that in the short term, the parameterized system preserves somehow reasonably well the momentums of all the flows in the original system. Where the bare truncated system, these curves are much different from the original ones. And here, the uncertainty increases due to the ocean drag noises. So we have the ocean equation for the ocean containing the noises. And these plots, these two panels showing the comparing of the small flows in the flow system and the superflows in the parameterized system. So we want to conclude here that the superflow parameterized system preserve in a short time reasonably well the momentums in both directions and also the angular momentums. To look into a longer term statistics, so on the contact forces. So with the same 18 flow setting, for the largest flow, we see here that first, we see that, okay, so let me first say that the contact forces here we are collecting are the contact forces for the largest flows from the small flows or the superflows. So this is only the partial contribution on the contact forces. For example, we take the one of the we take the largest flow, then the largest flow may have contact forces from the other large flows, right? And then there are contact forces from the small flows. So we only collecting these contact forces from small flows for the flow system. And for the parameterized system, we're collecting these contact forces from the superflows only, not from other large flows. So here the top row shows the contact forces for the largest flow. So first observation is that we see a highly non-Gaussian feature on the PDF, right? And then the parameterized system has a good match statistically with the full system. So we're covering this highly non-Gaussian statistics. And if the bottom row is the PDFs look into the all flows, like all the 6 largest flows. So here, this figure to conclude is that this parameterized system recovers this statistic accurate recovers this non-Gaussian features in the original system. So we obtain the statistic accuracy in the parameterized system. Similarly, on the other physical quantities. So here we are looking into the velocities in x directions, and velocity in 2 directions. We are considering 2 dimensions here. So velocity in x, angular velocity, yeah, and the momentum in x and the angular momentum. So here we are considering 3 different systems with the bare truncated system, parameterized system in red, bare truncated system in green, and the full system in blue. And then this black one is the normal fit. So we say that the full parameterized system resembles the full system. So in these features captured reasonably well. And the bare truncated system has different statistic behave. So meaning that this is not meaning that if we only consider the large flows in the system, it's not sufficient to characterize the flows in the region. So the reason is that in the bare truncated system, the contact forces from the small flows are just simply removed. So like the contact forces contributions from the small flows. So looking into the data assimilation side, let's consider the setting, the data assimilation setting. So we use the EAKF filter, so ensemble adjustment common filter, just for simple illustration purpose. The idea is to use a superflow based noise inflation. So once we parameterize the original system with superflows, we generate statistics on the contact forces, and then we no longer use the superfloes in the modern equation. We just use them as a noise inflation. So we no longer carry on this superfloes. This further reduce the computational cost, right? Because we don't have this calculations on the contact forces of the superfloes. And so how we do that? The idea is to do noise inflation with the noise inflation strengths, such as a standard deviation of the superflow to large flow contact forces. So this is statistic values based on one single long-term run of the forward model. And then performance, we look into the trajectories and like ocean currents, fields, and the skill scores. We mainly look into the skill scores of the root mean square errors and the pattern correlation coefficient. So here are simple ocean current recovery. So the left column here, panel A, showing the truth. So we are using truth, like the field looks like this in 20, 40, and 60 days. And then these are the assimilate ocean current using the Baire truncation in this column B, and using the superfloe based inflation, column C here. So we observe that this, if we simply remove the small flows, then the ocean current cannot recover. You see this velocity field is somehow completely different from the truth. Even the largest scale mode are not captured, right? And if we use the superflow based inflation technique, then we see that these large scale features are somehow recovered. So as you can see here, this eddy is reasonably well recovered, but there are some errors, right? This like, and a more realistic ocean current. So same thing that we have like more ocean mode, and then the superflow based inflation capture reasonably well, I would say, the truth, where the Baire truncation field in this case. So the skill scores, so we look into the root mean square error and the pattern correlation coefficients. So here, this figure shows a case, a simple case with 18 flows, where there are 6 large flows, and then there are 12 small flows. These 12 small flows are parameterized as 6 superflows. So here in the Baire truncation system is just the case using only the 6 large flows, the blue curve here, and the red curve just for the system with superflows. Superflow-based inflations. So with this simple superflow-based inflation, we obtain a much more accurate result, like much smaller root mean square errors. And this figure studies the skill scores with respect to the ocean uncertainty strength. So here, the ocean uncertainty, ocean noise is from 0.1 to 1. Similarly, we studied the skill scores with respect to the number of large flows kept in the system. So the Baire truncation in blue, red refers to the superflow-based inflation, and we see smaller flows when using this superflow-based inflation. Computational cost reduction. So in a single forward run, so if we consider like here 200 flows, in the full system there are 200 flows, so lots of contact forces calculations. And then in parameterized system, so there are 30 large flow and 30 superflows. So the computational time is significantly reduced in this case. Similarly for the data ensemble run, so and the Superfloe based inflation reduce the computational cost. And this is quite expected, right? Just be due to the less contact we need to calculate in the DM model. So the take-home message is follows. You don't need all the small flows to assimilate the large scale modes of the ocean, but you can simply ignore them. So this is the take-home message. So to conclude my talk, I introduced a superflow parameterization with a purpose focus on the data assimilation. So we develop a data assimilation framework and with the goal of gaining computational efficiency. So future directions, we would like to include and assimilate atmosphere wind modes, apply to more sophisticated DEM models, and look into more realistic applications like frame state simulation. Thank you. I'll stop here.